then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great.
Tis the season to be serving.
When I was solving equations, I was feeling amazing.
Okay, greetings calculus students. Welcome back and welcome to lesson number 2. So today's lesson is all about finding limits graphically. So yesterday we looked at finding limits from a numerical method, looking at tables. Today we're going to investigate finding limits looking at graphs. So from a graphical standpoint. And so we're basically looking at two things today. We're going to review what we covered yesterday. So we're going to look at some examples, some problems over the material that was covered yesterday. And then we're going to go over the process of finding limits for graphs. So generally how we'll begin each class, most days we're going to start the class by doing some type of review over what was covered the previous day, just to make sure we have a firm understanding of it. Sometimes that will come from problems that I will just create, as I will today. Other cases that may come from some of the harder problems from your assignment from the previous day. So I might pull some of the harder questions of the assignment of the previous day and use those problems to kind of review that particular concept. So let's go ahead and get started.
Okay.
So for today's lesson, I'm going to be going over 10 problems here. The first 4 are just review problems of what was covered yesterday. As you can see, number 1, we're looking at a table, so we're finding limits from table. And the last 6 are going to be over finding limits from graphs. So I'm going to use those examples that we're going to look at to kind of explain what we look at when finding limits from graphs. When it's all said and done, you'll see whether we're looking at graphs, whether we're looking at tables, whether we're looking at equations. The general premise of finding limits is the same across all platforms. But let's take a look at what we have today at the first example. So again, this is valuing limits from tables. For example, in this case, I'm finding the limit as x approaches -9. So what I need to see for there even to be an answer is I need to see as x gets very close to -9 from the left and very close to -9 from the right, I need to see a finite number that f of x is approaching. And if it approaches the same finite number from the left and the right, that answer is the limit. If it approaches 2 different numbers, or if it tends to infinity or negative infinity, the limit doesn't exist.
The limit does not exist. The limit does not exist.
What I'm concerned with more is the behavior of the function as x approaches -9. So again, when finding limits, we're looking at the value the function gets arbitrarily close to as the x value approaches the given value, not when the x value is equal to the given value. Now, there are many cases, as you'll see as we progress in limits, where the value of the function at the point is equal to the limit. In fact, that's the definition of being continuous at a point. So there's a lot of problems we'll investigate where the function is continuous at x equals c. And so the limit will equal the value of f of c. However, in a lot of other cases, that is not the case. So you can have a limit be some number and f of c not even be defined. You can have the limit be some number and f of c be a different number. And all of this you'll see today. Or f of c can be some number and the limit can still not exist. So you're going to see examples of all of those cases today, particularly when you look at graphs to kind of bring it home. But again, let's kind of look at this example here. So as I look as x approaches -9 from the left, so this is coming from the left, so the left means less than that value. You can see here that the f of x values appear to be approaching 5. So they appear to be approaching a finite number 5. So when the x values are very close to -9, if the f of x values are very close to some finite number, then we say that f of x is getting arbitrarily close to that particular number. So in this case, it's it's 5. That's from the left. We have to make sure there's agreement on the right. And if so, then that's going to be the answer. And so if I look on the right, So as x approaches -9 from the right, you should also see it's getting close to 5. So we have 5 on the left and 5 on the right. Therefore, the answer is 5. And that's really all you need to see when you're looking at tables. You need to see the same number from the left and the right. That's real important. And that's really what you're looking at, the values that the function approaches as f of x approaches the given value from the left and the right. Again, the value at the point is not that important, quite honestly. We're looking at the values as x approaches the given value from the left and the right. If that's a finite number and it's the same on the left and the right, that's the limit. If not, the limit doesn't exist. That's simple. Let's look at number 2. All right, so number 2, we're finding the limit as x approaches 1. And so again, at 1, it's undefined, big deal. We don't even care about that. We're looking at the behavior as x approaches 1. So as x approaches 1 from the left, -800, -1800, -7800. Wow. Okay. As x approaches 1 from the right, 800, 1800, 7800. Now again, look at these x values. These x values are very, very close to 1. Extremely close. But these f of x values, like this guy is 1,000 away.
What?
And this guy is 6,000 away.
What?
So it looks like the closer we get to 1, the space between the f of x values increases. And when you see that, so hopefully I think you can see that the f of x values is not approaching a finite number. There's from 800 to 1800 to 7800, there's no finite number you can say it's approaching. You can't say it's 7800 because that's the last number, because for it to be approaching 7800, the other numbers should be very close to 7800, which of course they're not. So when you see this action as x gets close to c from the left or the right, and you see the numbers getting increasingly bigger, we say that increases without bound, and it's going to infinity. So from the right here, it's actually going to infinity. So right there, that tells you the limit doesn't exist because it's not going to a finite number. But I want to just look at the behavior on the left as well. And so you see on the left, the values are getting increasingly smaller. So it's decreasing without bound, meaning it's going to negative infinity. So it's going to positive infinity on the left, negative infinity on the right, but either way you call it, the limit does not exist. So once again, for the limit to exist, f of x must become arbitrarily close to a finite number as x approaches c from the left and from the right. If that does not occur, the limit does not exist. Okay, let's look at example number 3. All right, so in this example, we'll find the limit as x approaches 5. And here you'll see here that f of 5 is defined. It's -3. F of 5 is actually defined. It's -3. Now don't get too happy, okay? Relax a little bit. Please don't assume that just because this value at 5 is defined, that's the answer. Because I promise you, I submit to you this day, that is not always the case. There are a lot of times where that is the case, but there are also a lot of times where that is not the case. Precisely as you're going to see on our next example. So, I mean, it's good to see f of 5 is -3. That's nice to see. But we're more concerned with the behavior as x approaches 5 from the left and the right, because that behavior is not always going to agree with the value at f of 5 or at f of c. So let's look at where we're going. So from the left, so as x approaches 5 from the left, these f of x values seem to be approaching -3, looking fine. And from the right, again, these f of x values seem to be approaching negative 3. So the answer is negative 3. Not because f of 5 was negative 3, but because f of x became arbitrarily close to negative 3 as x approached 5 from the left and the right. Okay, let's look at our last table example. And once again, you'll see we're finding the limit as x goes to negative 9, and you'll see that f of negative 9 is 6. Again, like, don't get so happy. That doesn't mean that's going to be the answer. So again, you have to look at the behavior from the left and the right as x approaches negative 9, not just the value at negative 9. And if you look very carefully, as x approaches negative 9 from the left, f of x is actually going to 8. And as f of x approaches negative 9, as x approaches negative 9 from the right, f of x is approaching 8. F of negative 9 is 6, but f of x is approaching 8 from the left and from the right. That means that the answer is 8. It doesn't mean that the limit does not exist. So just because the values that f of x approaches from the left and the right are different from the function at that particular value, doesn't mean the limit does not exist. So for the limit to exist, it just depends on the value that the function gets arbitrarily close to as x approaches c from the left and the right. It really has nothing to do with the value at c. All right, so now let's look at finding limits from graphs. And so these are going to be new problems. So these I'm going to explain as I go, but if you kind of understand what we've been doing with the tables, just looking at the values that the function approaches from the left and the right, we're essentially going to be doing the same thing just from a graphical standpoint. Okay, so here's our first graph problem. And so this represents the graph of f of x, and we're going to find the limit as x goes to negative 1. So we're finding the limit as x approaches negative 1. So we want to look at the value that f of x approaches. And so f of x is the same thing as y, so we're looking at y values. So we want to look at the y value that the graph is getting arbitrarily close to as x approaches negative 1 from the left and from the right. There needs to be agreement there for the limit to exist. So what I'm going to do, I'm going to first look at the left of negative 1. So here's negative 1 right here. I'm going to go to the left of negative 1. I'm going to get on the graph. So I'm on this particular graph. I'm on the left of negative 1. And I'm going to stay on the graph and approach negative 1. So here I'm on the graph and I'm approaching negative 1. And I get to negative 1. And I don't care if I have an open or closed circle at negative 1. Having a closed circle at negative 1 just means that the function is defined where that closed circle is. An open circle means it's not defined where that open circle is. But again, the value at c is not what we're concerned with. We're concerned with if f of x approaches the same finite value from the left and from the right. So when I'm looking at these graphs, and sometimes people get confused, open and closed circles mean nothing to me in terms of finding limits. Now, they mean an awful lot when it comes to continuity, something we're going to cover a little bit later. But in terms of finding limits, open circles, closed circles, rectangles, triangles, none of that stuff means anything. I'm just going to analyze the behavior of the graph from the left and from the right. So again, as I'm looking from the left of negative 1, I'm on the graph. I'm staying on the graph and I'm going to negative 1. And hopefully you can see as I go to negative 1 from the left, the y value is approaching is 2. So the y value is approaching is 2. So as I get closer and closer to negative 1, just look at the y values. As I get closer and closer to negative 1, they're becoming closer and closer to 2. Again, it doesn't matter if it was an open or closed circle here. They're also becoming closer and closer to 2. Well, let's look at the behavior on the right. So here's -1. So let me go to the right of -1. Let me hop on the graph. So I'm on the graph on the right of -1. And I'm going to stay on the graph, and I'm going to approach -1 from the right. And hopefully you can see as I approach it from the right, it goes to the y value of 1. So I was at 2 on the left, 1 on the right. What does that mean? That means the limit does not exist. Again, for the limit to exist, you have to be approaching the same finite number from the left and from the right. Okay, let's look at another example. So the next example, I'm going to keep the same graph, but I'm just going to find the limit as x goes to +1. So there you can see the same graph, and here we're finding the limit as x goes to +1. So here is +1 here. And again, when finding these limits, please don't get worried about these open and closed circles. They're important for continuity. They're important for finding the value of the function at that particular point, but they're unimportant when it comes to finding the value of the limit. So here's 1 here. Let me go to the left of 1, jump on this graph, and stay on this graph as x approaches 1 from the left. And hopefully you can see as x gets closer and closer to 1, the graph gets closer and closer to the y value of 5 from the left. And also from the right, as x gets closer and closer to 1 coming from the right on the graph from the right, hopefully you can see it approaches the y value of 5. So from the left it's going to 5, from the right it's going to 5, so the answer is 5. Now on this function, f of 1 was actually 3. F of 1 was defined, f of 1 is actually 3. But the limit of f of x as x goes to 1 is 5. And again, those things do not have to be the same, as we illustrated when we looked at the tables. And what it means, when the limit is different from the value at the point, it just means the function is not continuous at that point. Something we'll get into a little more formally on another day. But for right now, if the limit as x goes to c of f of x is not equal to f of c, it just means f of x is not continuous at x equals c. All right, let's look at another graph example. So here we have an example. So on this one, again, this is the graph of f of x, and we're finding the limit as x goes to 1. All right, so I want you to look at this one and see what you think the answer is. If you need a little bit of time, pause the video, because after 2 seconds, I'm going to go ahead and talk through the solution. But I really want you to look at this first before I talk through the solution. So pause the video, take a second, see if you can figure out what you think the answer is, and then you'll hear me display the answer. All right, so we're finding the limit as x goes to 1. Here's 1 here. So coming from the left of 1, I'm going to 5. Coming from the right of 1, I'm going to 5. So the limit is 5. Some of you may say, but there's no closed circle. You may say over here on the previous problem, there was at least a closed circle somewhere. You're saying here, there is no closed circle. Big deal. Since there's no closed circle, all that means is f of 1 is not defined. It's like those problems in the table where under the value it had an error or said undefined. That's all it means. It just means f of 1 is not defined anywhere. But again, that doesn't affect the value of the limit. As long as we're approaching the same value from the left and the right, that value is the limit. The value of the function at the point, whether the function is even defined at the point, has no bearing on the value of the limit. So that answer should be 5. All right, let's look at the next example. So there's the next example. Again, so for these last 4 examples we're going to do, I want you to pause the video and try it. And then when you feel like you got it, unpause the video and you listen to me walk through the solution. So for this particular problem, again, this is the graph of f of x. We're finding the limit as x approaches 0. So at this time, pause the video and see if you can find the answer. All right, so hopefully you were able to come to some conclusion for this particular problem. And now we're finding the limit as x goes to 0. So I'm going to do the same thing I've been doing all day. I'm going to look at what happens as I go from the left and from the right. So here is 0. So I'm going to go to the left of 0. I'll hop on this graph. Here I am on the graph. I have to be on the graph. And I'm going to approach 0. So this is approaching 0 from the left. So I'm just staying on the graph and letting x get closer and closer to 0. And as x gets closer to 0, you may notice I'm not really stopping at a particular finite number. It's not like I'm stopping at -5 right here because this is an arrow, so that means it's still going down. So actually on this problem, as x approaches 0 from the left, f of x is going to -infinity. So the closer and closer I get to 0, the more the graph goes down, and it goes down to -infinity. If you look from the right of 0, so here's 0, so here I am to the right of 0, here I am, I hop on the graph, and now I'm getting closer and closer to 0 from the right. You should notice the graph is going up to positive infinity. Went to -infinity from the left, positive infinity from the right, but because it was infinite, it means the limit does not exist. And you need to be a little bit familiar with this type of action. Again, we cover continuity and discontinuity a little bit later, and we get a little more formal with this. But since we're seeing that, I do want to kind of address some of the things we've seen thus far. When you see this action where as x approaches a number, a graph shoots straight down or shoots straight up, that's an indication of a vertical asymptote, or what is called an infinite discontinuity. So anytime you see a graph and you see it shoot straight down or shoot straight up at a particular x value, that is an indication of a vertical asymptote or an infinite non-removable discontinuity. And just to go back, just to point a couple of things out. And again, right now I'm going to ask you to be able to classify these discontinuities because we're going to cover continuity and discontinuities, I believe 2 lessons from now. But since we're looking at them, I do want to point them out so when we do cover them formally, you're somewhat familiar. You'll notice here, when you just have this little hole, sometimes that's called a point discontinuity. Mathematics, generally we name things very appropriately. Like for instance, these guys were going to infinity and -infinity as x approaches 0. That's called an infinite discontinuity, also a vertical asymptote. Here, you have a little point here, just a little missing point. And that's called a point discontinuity. It's also called a removable discontinuity. And if we go back to the previous graph, so that there's 2 things happening on this graph. So here again, you have this point, and even though it's defined at another spot, that's still called a removable or a point discontinuity, even though it's defined here later. And if you look at this action on -1, you can see how the value of the function kind of jumps from 2 to 1. Like it jumps from one value to another value. And that's called a jump discontinuity. So again, 2 lessons from now, we'll get into those things a little more formally, but just kind of want to point them out as we're looking at them. Okay, here is the next example. So this example, we're finding the limit as x approaches 3. So pause the video and give it a try. All right, so hopefully you're able to maneuver this one. Again, you should be a little more used to this stuff, so I'm gonna go to this fairly quickly. So coming from the left of 3, I'm going to -1. Coming from the right of 3, I'm going to -1. Again, I'm not concerned with this closed circle at -2, so my answer is -1. And our last example for today, we're going to use the same graph, but we're going to find the limit as x goes to -1. So here we are, same graph, we're finding the limit as x goes to -1. Again, pause the video, give it a try, and then I'll go over it with you. All right, so hopefully you're able to see this one. So coming from the left is going to 1, coming from the right is going to 2. So it's going to 2 different numbers. So the limit does not exist. So another thing I want to point out, I'll just point out now, which we'll cover again more formally a little bit later. Where you have the x values, where you have jump and infinite discontinuities, the limit doesn't exist. The x values where you have removable discontinuities, the limit does exist. So something to keep in mind, something to keep in your toolbox as we maneuver. All right, so I want to pause there. Hopefully after lesson 2, your understanding of limits has increased, and hopefully you feel very comfortable at this point finding limits from tables and finding limits from graphs. There will be an assignment which will have both those things on it, and hopefully you do well on that particular assignment. Tomorrow we'll begin to look at finding limits analytically. That's finding limits utilizing algebra, basically. So finding limits from an algebraical analysis. So I hope you found this lesson intriguing and interesting and thought-provoking and important, and we'll see you next time.
Specialized in science and mathing, original black men, busting thoughts that pierce your mental, the fierce, ripping your section, vocal toe to toe, impeccable, splitting your back, son. Simple as addition and subtraction, black thought.